Thought I'd show you guys something today. This is one of my patent models. It's actually a tuning capacitor for Tesla coils. But my tabby cat Absinthe will probably steal the show because she's chasing her tail like a dog. But anyway, we go back to here. So this is a pretty simple thing. It's a capacitor bank where the sections are tapped to the place digits of binary numbers. And so there's a stack of 16 capacitor banks over there. And over here is just an array of switches which put them in the circuit or remove them. And so we start off with 1 nanofarad, and then 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16384, and the last one is 32,768. And so by adding these to the circuit, you have from 0.001 microfarad up to 65.536 microfarads. Now for most Tesla coils, this range is much too large, but it's very useful for also tuning induction coils. So what I have here to test is a very simple high-frequency induction coil, and it's very similar to the one Tesla used in his 1891 lecture and in the book Experiment with Alternate Currents. And there are two secondary coils in this one. Each one has about 300 turns of wire. And then the primary coil is wound on the inside, and it has 100 turns of wire. So there's only a 6-to-1 turn-to-turn ratio in this high-frequency coil. And over here is a kicking coil, which is nothing more than an electromagnet and an interrupter. And it runs from AC or DC. I'm running it just from mains voltage right now. And it's just a way of supplying about a 1,000-volt pulse to the primary coil. And again, this is just for tuning purposes to see what size condenser or capacitor we need. So I'm going to start off with just a random switch. This is 128 nanofarads, so it's a 0.128 microfarads, and that's a very typical range for a very small kind of kicking coil like this. And if I advance the interrupter, you see just a little tiny spark, and that means frequency is too low. And when frequency is too low, that means the capacity is too big. Now I'm just going to hit the lights so we can see this better. So as I mentioned, frequency is too low, so we're going to turn that one off, and we're going to turn the next one. So this is 0.064 microfarads. And turn it on. We see if we get better or worse. So the spark grows a little bit. It's about 1 inch long now. But I still don't think it's quite in resonance. So we're going to keep going. Turn it off. Now this is 0.032 microfarads. Spark is improving. Getting about a 2-inch spark there. So we're going to go with 0.016. That's looking better. Now, this is 8 nanofarads. Now we see the spark diminishes. So that means that we're too high a frequency. It means we need more capacity. So the 16 worked pretty well. So what we can do now is start using the binary sequences here. And what we can do is we can try 4 plus 8, which is 12. And let's see what happens. Nope. Still not enough. So, you get the idea here of what we're doing. I happened to do a test earlier, and 0.02 microfarads is kind of what this coil wants. This was the maximum spark I was able to get. Now, with this kicking coil circuit, it's not the frequency that these like to operate at, so it's very inefficient right now in how it's operating. So, even though it's operating inefficiently, now I know what size capacitor I need for a typical spark gap circuit. Because in this case, the inductance is fixed. With the usual style coils, there's normally a tapped primary, so you can tune with a combination of the capacitor and the inductance in the primary coil. But in this case, it's fixed. In a lot of pancake coils, they're embedded in wax. You might not even know the geometry. So this is how you're able to figure that out in a very simple way. Now, if you'll notice, this kicking coil produces not quite 1,000 volts into the primary coil. And so if you were to look just for them from the turn-to-turn ratio, 6:1, we could expect 1,000 volts in and maybe 6,000 volts out. We're seeing a lot more voltage here because with resonant systems, it's based on resonance. It's not based on turn-to-turn ratios like usual low-frequency transformers are. So you're not getting any more power out than what you put in. In fact, this one's operating very inefficiently, but you are able to get sometimes higher voltages using less wire. And that was kind of the point of the Tesla coil to begin with, because to make this sort of spark with an induction coil, you might need 2 or 3 miles of wire in it. And this has just a few ounces.